Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. I was in major U.S. newspapers such as the June 20, 1990 issue of the Wall Street Journal because I contributed new calculus to modern calculus and because I contributed new algebra to extreme scale algebra and because I invented a never-before-seen computer for parallel processing computer science. I was the cover story of top mathematics publications, such as the May 1990 issue of the SIAM News. The SIAM News is the most widely read mathematics news journal. I was the cover story of top mathematics publications, not because of my good looks, but because of my contributions to mathematical knowledge, namely 9 never-before-seen partial differential equations of modern calculus that I invented. Back in 1989, I was in the headlines because I mathematically and experimentally discovered how to solve the most extreme scaled problems arising from the system of partial difference equations of modern algebra. That system of partial difference equations approximates the system of coupled nonlinear time-dependent and state-of-the-art partial differential equations of modern calculus. That system of partial differential equations in turn encodes a set of laws of physics that governs the motions of fluids. I was in the headlines because I mathematically and experimentally discovered how to massively parallel process and how to communicate synchronously and how to compute simultaneously and how to do both across my new internet, that is a new global network of 65,536 tightly coupled processors, with each processor operating its own operating system, and with each processor having its own dedicated memory that shared nothing between each other. That is a new supercomputer, and that is a new computer. I was in the headlines because I mathematically and experimentally discovered how to solve the toughest problems arising in the most extreme scaled algebra and how to solve them on the most high performance massively parallel processing supercomputer, and how to use that new knowledge in extreme scaled algebra to look a mile deep into an oil field and help recover otherwise unrecoverable crude oil and natural gas. My country of birth, Nigeria, benefited immensely from the technology that is used to discover and recover crude oil and natural gas. The modern high-performance supercomputer that derives its power from communicating and computing across millions upon millions of tightly coupled commodity processors is the digital divining rod that provides visibility inside the darkness of the mile-deep oil fields of the Niger Delta region of southeastern Nigeria. In modern times, the petroleum industry purchases 1 in 10 supercomputers and purchases those supercomputers because the supercomputer earns money, saves money, and pays for its $100 million price tag. The modern supercomputer now draws its computing power by supercomputing many things at once or in parallel, instead of computing only one thing at a time or in sequence. Back in 1989, it made the news headlines that a lone wolf African supercomputer wizard in Los Alamos, New Mexico, United States, has discovered how to compute the solutions of extreme scale system of equations of algebra that arises from simulating the motions of injected water, crude oil, and natural gas that are flowing across production oil fields. I, Philip Emeagwali, was that African supercomputer scientist that was in the news for discovering how to solve the largest system of equations of modern algebra and for discovering how to solve them at once or in parallel instead of solving those equations only one equation at a time or in sequence. I was in the headlines because I discovered how to solve 65,536 sets of equations of modern algebra and how to solve those equations across my new internet that is a new global network of 65,536 tightly coupled commodity processors that shared nothing between each other. I was in the news because my mathematical discovery changed the way we solved the toughest problems arising in extreme scale algebra. In the old way, we solved many algebraic problems and solved them one at a time. We solved grand challenge problems in sequence and solved them within only one isolated processor that was not a member of an ensemble of processors that communicates and computes together and as one seamless, cohesive supercomputer. In my new way that made the news headlines in 1989, I discovered how to solve a set of 65,536 algebraic problems that each comprised of a system of 366 equations of algebra and each with 366 variables. I discovered how to solve the most extreme scaled problems arising in algebra. And I discovered how to simultaneously solve those problems and solve them across those 65,536 processors or solve them in parallel. Before my experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July 1989, parallel processing, was controversial and was widely dismissed as a huge waste of everybody's time. Parallel processing, the technology that powers the modern computer and massively powers the high-performance supercomputer, rests on the intellectual confidence that was gained from that new knowledge that arose from my discovery that occurred on the 4th of July 1989. After my experimental discovery of 1989, the once controversial parallel processing became grounded in practical confidence or practical knowledge. It's practical knowledge because parallel processing is embodied inside every computer, inside nearly every computer, and inside all supercomputers. It's practical knowledge because parallel processing is at the foundation of extreme-scale computational physics, as well as computational mathematics. It's practical knowledge because parallel processing is used to foresee otherwise unforeseeable climate change. Global warming is a disaster in waiting that is looming on the horizon, but that can be foreseen more accurately with a massively parallel processing supercomputer that I invented. As an extreme-scaled computational mathematician that came of age in the 1970s and 80s, my grand challenge was to show that what's impossible to compute for the computational physicist that is computing with the fastest processor is in fact possible to compute for the massively parallel processing supercomputer scientist that is supercomputing and computing across the slowest 65,536 processors in the world. As a large-scale algebraist who is an expert in solving the largest system of equations arising in algebra, I focused on the structure and on the form of my world record system of 24 million equations of algebra that was a world record in 1989. In the petroleum in reservoir simulation codes of the 1950s, 60s, and 70s, the technique of choice for discretizing the governing partial differential equations for crude oil and natural gas recovery is called the alternating direction implicit finite difference method. In modern textbooks on finite difference discretizations of partial differential equations, the alternating direction implicit method is also recommended for solving the heat equation that is the poster boy of parabolic partial differential equations. The alternating direction implicit method yields a tridiagonal system of partial difference equations of algebra, or a system in which its companion square matrix has non-zero elements only on its diagonal row of entries, and along its subdiagonal row of entries, and along its superdiagonal row of entries. A tridiagonal system of partial difference equations of algebra is impossible to solve in parallel, or to solve by processing many things or processes or equations at once. A tridiagonal system of partial difference equations is only possible to solve in sequence or to solve by solving only one equation at a time. 65,536 subsets of a tridiagonal system of partial difference equations cannot be emailed synchronously and or solved simultaneously. It's impossible to do both across a new internet, that is a new global network of 65,536 tightly coupled processors that shared nothing between each other. My contribution to computational mathematics was that I discovered how to reformulate the tridiagonal system of partial difference equations of extreme scale algebra that is used in the petroleum industry and used to achieve the highest resolution in the petroleum reservoir simulators that are used to recover otherwise unrecoverable crude oil and natural gas. The tridiagonal system of partial difference equations of extreme scale algebra arose from implicit finite difference discretizations and approximations of the governing system of partial differential equations of modern calculus. Implicit finite difference approximations allow long time steps which compress the amount of floating point arithmetical operations that will be executed. However, the tridiagonal system of partial difference equations of extreme scale algebra cannot be solved in parallel. On the other hand, the diagonal system of partial difference equations of extreme scale algebra obtained from explicit finite difference discretizations of the governing system of partial differential equations of modern calculus only allow short time steps, which in turn increase the amount of floating point arithmetical operations that will be executed. The short time steps of explicit finite difference discretizations is determined by the Courant condition that prescribes the relationship between the length of the spatial time steps and the temporal time steps, and the wave speeds. The computational fluid dynamics model loses its mathematical accuracy when its time steps cannot account for the small scale factors that affect the fluids flowing across the surface of the earth. For these reasons, explicit finite difference discretizations are more computation intensive than implicit finite difference discretizations. In other words, short time steps means more time steps to keep the system of partial difference equations of extreme scale algebra from falling apart or becoming unstable. I preferred explicit finite difference approximations because their diagonal systems of partial difference equations of extreme scale algebra can be solved in parallel. I theoretically discovered how to reformulate my system of partial differential equations of modern calculus into a diagonal system of partial difference equations of extreme scale algebra that approximated them and that enabled me to solve 65,536 problems at once. I was asked to describe how extreme scale algebra is used in day-to-day life in Nigeria, in Africa. In my country of birth, Nigeria, and in any oil-producing nation, the largest possible systems of partial difference equations of extreme scale algebra must be solved as a precondition to discovering otherwise undiscoverable crude oil and natural gas. The dense, abstract, and invincible large systems of partial difference equations of extreme scale algebra are the common denominators across all supercomputers that were ever built. And 1 in 10 supercomputers ever built were purchased by the petroleum industry. The high-performance supercomputer is used to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas from the Niger Delta oil fields of the southeastern region of Nigeria. The supercomputer contributes to Nigeria's economy. The larger the system of partial difference equations of extreme scale algebra that computational mathematicians can solve, the more oil money they can contribute to build schools and hospitals in Nigeria. The fundamental question at the crossroad of the frontier of the largest system of equations of extreme scale algebra and the frontier of the most massively parallel processing supercomputer is this: can a network of 8 processors that is the heartbeat of the modern computer be harnessed and used to solve the largest system of partial difference equations of extreme scale algebra? Large systems of partial difference equations of extreme scale algebra arise from our societal needs to make our world a better place and a more knowledgeable one. Large systems of partial difference equations of algebra arise from general circulation modeling, and general circulation models are used to forecast and to foresee otherwise unforeseeable global warming. Large systems of partial difference equations of algebra arise from our need to recover otherwise unrecoverable crude oil and natural gas, and to recover them by using computational physics codes and using those codes to hindcast the motions of crude oil and natural gas. The Oloibiri oil field of Bayelsa State of southeastern Nigeria is the first oil field in West Africa. The Oloibiri oil field was abandoned in 1978. Like all abandoned oil fields, the Oloibiri oil field was abandoned merely 20 years after it was discovered. Like other dried up oil fields, the Oloibiri oil field was not dried up in a literal sense. About 70% of the crude oil discovered in Oloibiri remains unrecoverable and remains in Oloibiri. That 70% was abandoned because that 70% will cost 71% to recover. I was asked, how do we recover crude oil and natural gas? Briefly, to increase the crude oil and natural gas recovered from the Niger Delta oil fields of the southeastern region of Nigeria, water is pumped into each oil field. Massively parallel processing supercomputer simulations are used in advance and used in Nigeria and used to help petroleum engineers that depend on the unreasonable preciseness of the laws of motion of physics. To the extreme-scaled computational physicist, simulating across millions upon millions of tightly coupled commodity processors, the set of laws of physics is the magic sword or the hero's sword. That magic sword is not physical. That magic sword is intellectual. The massively parallel processing supercomputer is the divining rod of the petroleum geologist. That massively parallel processing supercomputer rod is imbued with the magical power of a system of partial difference equations of extreme scale algebra that was formulated from a companion system of partial differential equations of modern calculus that embodied a set of laws of physics. Large-scale partial difference equations of extreme scale algebra solved at the fastest massively parallel processed supercomputer speeds is the new mathematical knowledge that is used to understand the best ways to pump water into the oil fields of the Niger Delta region of southeastern Nigeria. Pumping water into production oil fields drives the most crude oil and natural gas towards the crude oil and natural gas production wells. Back in the 1980s and earlier, the 25,000 vector processing supercomputer scientists in the world that had Seymour Cray as their spokesman were demanding an experiment-verified proof that they could massively parallel process across billions upon millions of tightly coupled commodity processors. Seymour Cray and those 25,000 vector processing supercomputer scientists were not impressed by big ideas about the massively parallel processing supercomputer or deep theories on how to solve the toughest initial boundary value problems and how to solve them in theory but not in practice. In 1989, it made the news headlines that a lone wolf African supercomputer wizard in Los Alamos, New Mexico, United States, had invented the massively parallel processing supercomputer. I am that supercomputer scientist that invented the parallel processing technology and invented it as a new internet and as a new global network of 65,536 tightly coupled commodity processors that shared nothing between each other and that can be used to solve in one day the most computation-intensive problems arising in physics and solve in one day one of the toughest problems arising in computational physics and solve in one day what formerly took 65,536 days or 180 years of time to solution. I, Philip Emeagwali, was that African supercomputer scientist that invented how to massively parallel process and massively compress 180 years of time to solution to only 1 day of time to solution. I invented the Philip Emeagwali formula that then US President Bill Clinton reconfirmed in his White House speech of August 26, 2000. Before my invention, parallel processing solved the toughest problems in theory, but not in practice. Before my invention, it was commonly said that parallel processing is good in theory, but not in practice. I immortalized parallel processing in the computer. Solving the toughest problems arising in mathematics and physics and solving them across a new internet do not work out the same way for solving the same problem on a computer. The outcomes of theorized massively parallel processing are different when putting theory into practice. A supercomputer theory should be a subset of reality. I began my quest for the largest system of equations of algebra that can be solved on June 20, 1974. I began my quest at the frontier of large-scale algebra, and I began that quest by solving the largest systems of equations of algebra that I could solve on the fastest supercomputer in the world. I began my quest with a tridiagonal matrix algorithm for finite difference equations of extreme scale algebra. That tridiagonal matrix algorithm is a simplified Gaussian elimination algorithm that is described in algebra textbooks. That tridiagonal matrix algorithm is 2 orders of magnitude more efficient than the Gaussian elimination algorithm applied to non-sparse and non-structured matrices, or applied to dense matrices that had entirely non-zero elements. That tridiagonal matrix algorithm is valid only for diagonally dominant matrices. I began my quest in extreme scale computational mathematics, and I began that quest by solving extreme scale systems of partial difference equations of algebra and solving those equations on a sequential processing supercomputer. That supercomputer was at 1800 Southwest Campus Way, Corvallis, Oregon, United States. In the mid-1970s and at 7 in the morning, I parked my red 2-speed bicycle in the bicycle rack that was behind Kidder Hall at 2000 Southwest Campus Way, Corvallis, Oregon, United States. I parked 200 feet away from the sequential processing supercomputer that I was programming. I had been supercomputing since June 20, 1974, and since age 19, and therefore I should not be described as an overnight success. On the 4th of July 1989, I invented the massively parallel processing supercomputer. I invented that technology after 15 years of supercomputing alone. My invention of how to solve a then world record system of 24 million partial difference equations of extreme scale algebra made the news headlines because it was an invention that opened the door to extreme scale algebra. I invented the massively parallel processing supercomputer, and I invented the technology only after the community of 25,000 supercomputer scientists that were led by Seymour Cray had given up on the massively parallel processing supercomputer. I invented the massively parallel processing supercomputer, and I invented the technology as heralding the end of vector processing supercomputers. My invention was a paradigm shift because it forced 25,000 supercomputer programmers and their leader Seymour Cray to abandon their vector processing supercomputers and embrace the modern supercomputer that is powered by parallel processing technology. I'm Philip Emeagwali. I invented the massively parallel processing supercomputer, and I invented the technology as the starting point of the mass production and the commercialization of parallel processing computers and massively parallel processing supercomputers. Parallel processing enables the modern supercomputer to do more than 10 million things at once. Unlike the 25,000 vector processing supercomputer programmers of the decades of the 1970s and 80s, and the sequential processing supercomputer programmers of the decades of the 1950s and 60s, I ignored the widespread skepticism that parallel processing is a huge waste of everybody's time. I ignored the warnings of the leaders of thought that was published in the June 14, 1976 issue of the Computer World. The Computer World was the intellectual mouthpiece of the computing community. That issue of the Computer World carried an article titled, quote, "Research in Parallel Processing Questioned as Waste of Time," unquote. The sequential processing supercomputers that I programmed back in 1974 only executed floating point arithmetical operations and executed them on pairs of numbers. A sequential processing supercomputer computes in sequence or by computing only on only one pair of numbers at a time. For my first sequential calculations of the mid-1970s, I used the algebra textbook technique called Gaussian elimination. That technique is described in textbooks on linear algebra. I used a variant of Gaussian elimination that required no pivoting. I used that variant of that classic algebraic technique to solve my system of tridiagonal or three-diagonal equations of algebra. My tridiagonal equations arose from the computational physics codes that I wrote for sequential processing supercomputers that I was programming in the 1970s. I wrote those codes for hindcasting the motions of crude oil, injected water, and natural gas that flows through a porous medium. This includes the motions of crude oil and natural gas that flow towards production oil wells. An oil field or a water aquifer is defined within a porous medium. Put differently, the oil field is comprised of voids called pores that are filled with crude oil and natural gas that flow across the voids and flow towards the production oil wells. If this extreme-scaled petroleum reservoir simulation technique was executed across a massively parallel processing supercomputer, was applied back in 1958 and applied to recovering crude oil and natural gas from Oloibiri oil field in Bayelsa State, Nigeria. That oil field, that was the first oil field that was discovered in West Africa, would not have been abandoned in 1978 or abandoned merely 20 years after it was discovered. I'm Philip Emeagwali. I am the mathematician and the physicist that invented how to solve the toughest problems arising in modern calculus, extreme-scale algebra, and computational physics. On the 4th of July 1989, and in Los Alamos, New Mexico, United States, I invented the precursor to the massively parallel processing supercomputer of today. My new supercomputer is the technology that enables the most accurate simulations demanded for extreme-scaled computational physics within a multidisciplinary environment. I am well known as the supercomputer scientist that contributed to the development of the modern computer, but I am not known well as the mathematician that contributed new equations to modern calculus and extreme-scale algebra. I am well known for my invention of the massively parallel processing supercomputer, but I am not known well for how my invention changed the way we look at the modern computer. I am well known for my invention of the high-performance supercomputer, but I am not known well for the rich and fertile consequences that my invention brought to the supercomputer industry. I am well known, but I am not known well. Thank you very much. I'm Philip Emeagwali. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.